KH for Weibel's homotopy K-theory and also on related results on K-theory itself. Certain refinements of Barwick theorem of the fact. Okay, so just a general plan of the talk. Well, I will talk mostly about small categories with bounded structures, but in the preprint, the results are proved in a more general context of dualizable categories, and I will briefly mention this more general context. But mostly to explain the ideas, I will focus on small categories because they're just easier to understand. Equivalently, this means that we consider dualizable categories, but those which are compactly generated. So it's basically equivalent setting. First, I'll formulate the results themselves and then briefly explain some interesting constructions which are used in the proofs. And just a reference for all of this is a recent preprint which I uploaded on archive in March. Just a general kind of paradigm, at least for the beginning of this talk, I will recall some results which are quite familiar for connective Ivan ring spectra, and they turn out to be dual to some of my results, which is quite surprising duality, quite surprising analogy. And so these results for connective Ivan ring spectra, they can be equivalently formulated for bounded wave structures. So this is terminology of Bandarka. But I mean, it's essentially the same thing to talk about bounded wave structures or just to talk about connective Ivan rings. And these bounded wave structures are kind of Cauchy dual to bounded structures. So this is like the basic intuition. But it turns out that this is not just intuitive Cauchy duality, but the formulations of the results will look like we're really doing some kind of duality on the level of spectra. I mean, some kind of Anderson duality, but not really. So this is just an intuition to better understand what's going on. So just very briefly, I recall kind of the main player. I will call them small t categories. So small t category is a small stable infinity category with a bounded T structure. So we have a small stable category and a pair of full subcategories. I will use the homological grading. So this is like connective part and co-connective part, such that the mapping space vanishes. Here, maps, of course, means mapping space, not the mapping spectrum. I mean, this condition also can be formulated on the level of homotopy categories. So for any object, there is a K-fiber sequence with first object connective and another object is co-connective shifted by -1. And C is generated by the heart as a stable subcategory. So the later condition is boundedness of the T structure. So this is like the main player for the talk, kind of the basic object which we'll be dealing with. And we use a standard notation for like C greater or equal to A is the same as C greater or equal to 0 shifted by A, and so on. So C from A to B is like objects with homological amplitude between A and B. And in particular, we have the heart, which is like C from 0 to 0. So this heart is abelian category, and we have a unique after isomorphism exact functor from derived category of the heart, bounded derived category, to C, which extends the inclusion. So this follows, for example, from the universal property of bounded derived category of small abelian category. And yeah, I mean, if you first learn about the structure in the context of triangulated categories, then for abstract triangulated categories, there might be a problem with this realization functor. But here, for stable categories, there are no issues at all. It's kind of automatic from the universal properties. Okay, so this is like the main player on when we talk about T structures. Okay, so now, as I promised, I will recall some familiar results for connective Ivan rings. And so basically, one of them is Waldhausen estimates on connectivity. So Waldhausen considers simplicial rings and connective K-theory, and the more general statement was proved by Land and Tamme for connective ring spectra. So we consider the following situation. So we have a non-negative integer n and some map of connective even rings. With this condition, so this condition basically says that cone of F is n-connective, cofiber of F is an n-connective spectra. So we have isomorphism in degrees less or equal than n-1 and epimorphism in degree n. I'm sorry, it means that fiber is n-connective. Yeah, fiber is n-connective. Okay, so if n equals 0, we additionally require that the ideal is nilpotent. And then under these assumptions, the induced map on K groups is isomorphism in degree at most n and epimorphism in degree n+1. So this is like the well-known connectivity estimate. And here the proof, of course, uses I mean, there are several ways to prove it, but basically they use explicit K-theory space. You need some kind of model of K-theory space, basically, for example, BGL and take plus construction. So this result is proved on the level of K-theory spaces. And for non-positive K groups, it's kind of easier, an easy exercise. Okay, so this is a general Waldhausen's estimates, and there are special cases. So I'm spelling them out because they will be interesting analogs for this for T structures. So one situation is when S is just pi 0 of R, and we assume the vanishing of homotopy groups of R in degrees from 1 to n. So of course this assumption always holds for n equals 0 tautologically. And then the map from K-theory of R to K-theory of pi 0 is isomorphism in degrees at most n+1 and epimorphism in degree n+2. And also we have a corollary for ordinary associative unital rings. So if you have nilpotent extension of rings, then the induced map is on K groups is isomorphism in degrees in non-positive degrees and epimorphism in degree 1. So these are all kind of standard. And these estimates are well known to be sharp, even if we work just over a field. And it doesn't matter which field we choose over any base field, these estimates are sharp. And by the sharpness, I mean that the map, which is an epimorphism, is in general not an isomorphism, so it has non-trivial kernel. So this is easy to show. This sharpness by examples. Okay, so now it turns out that if we just very naively formulate the dual versions of the statement, that then they turn out to be correct, but the proofs are completely different. So basically, we just replace pi j for all the relevant spectra with pi -1 minus j. And also replacing epimorphisms with monomorphisms. Equivalently, we're replacing connectivity condition on the co-connectivity condition. So one result is the following. So we have a exact functor between small stable categories such that the image generates the target as an idempotent complete stable subcategory. And for any objects, the map on X groups is an isomorphism in degrees at most n-1 and monomorphism in degree n. And then the induced map on K groups is an isomorphism in degrees starting from -n and the monomorphism in degree -n-1. So this is like not just kind of the theorem of the heart, but it's just a functor between two different categories with bounded T structures.
Sorry, may I ask a little question? What is the analog in this context of the nilpotency of the kernel?
Analog of nilpotency is the condition that the image of F generates D. Basically, because like the nilpotency condition was required only in the case n equals 0 in the previous theorem. So here, kind of the analog of this condition is that when n equals 1, then the heart of D might be bigger than the heart of C, but this is a situation of devissage. So on the level of hearts, we have a situation of devissage, and this is kind of dual to having a nilpotent extension on the level of pi 0. So this is analog. So pi 0 is analogous to the heart, and nilpotent extension is analogous to situation of devissage for abelian categories.
Okay, thank you.
Okay, just to recall that this statement was of course known for connective K-theory by the Barwick theorem of the heart and by equivalence devissage theorem. So again, equivalence devissage is needed only when n equals 1 in this result. And it was also known for minus first K group, and more precisely, we just have the vanishing of this minus first K group. This is a result of Anciot, Gepner, and Heller. But surprisingly, I will mention this later, for the legible categories, we actually don't have the vanishing of minus first K group, but still the result holds. The properly formulated result holds. Okay, and assertions about K minus 2, K minus 3, and so on are completely new. I mean, except for the case when the heart is Nasserian or Artinian. Well, more generally, there is like a stably coherent situation, but I mean, without some very strong assumptions on the heart, these results are completely new. But for example, if the heart is Nasserian, then it is known that negative K groups just vanish in all degrees. Okay. Now I mentioned the corollary. So the first corollary is kind of similar to the corollary which was comparing the K-theory of R and K-theory of pi 0. So suppose that for some n, we have isomorphism on the X groups between the object. So the realization functor induces isomorphism on X groups in degrees at most n. And then the maps on K groups are isomorphism in degrees starting from minus n minus 1, and the monomorphism in degree minus n minus 2. And these estimates turn out to be sharp. For all n, this estimate is sharp. And we will give an example for, if time permits, we will give an example for n equals 1. So it basically says that the naive K-theoretic theorem of the heart, it fails for in degree minus 3. So we always have theorem of the heart in degree starting from minus 2, just by this corollary. But for K minus 3, in general, it fails. And already over a field. If you work with DG categories over a field. Okay, and another corollary is for a refined version of devissage. So if you have a situation when we have fully faithful exact functor such that its image generates the target by using extensions, then the induced map is an isomorphism degree starting from minus 1, and the monomorphism in degree minus 2. And again, we will give an example when the map on the minus second K group is not surjective. Okay, now I recall again a result about connective Ivan rings, which is basically a very well-known celebrated result of Dundas-Goodwillie-McCarthy. So there is this localized invariant, which I think there are different notations for it, but for example, it can be denoted as K-inf. This is the fiber of the cyclotomic trace, the map from K-theory to topological cyclic homology. The statement is that for a connective Ivan ring, the map from K-inf of R to K-inf of pi 0 is an equivalence of spectra. And more precisely, as probably many people in the audience know, this of course holds for a quotient of pi 0 by an nilpotent ideal, but this is automatic by a general result of Land and Tamme on truncated localized invariants. If you have this property, like which is formulated here for K-inf, then you automatically have nilpotent invariance on the nilpotent extensions. Okay, now I formulate the dual result, and for now it's not obvious that it's dual. So this dual result says that if you have a small T category, then the realization functor gives equivalence of spectra between KH of the heart and KH of C. So KH here is the Weibel's homotopy K-theory. So originally it was defined for, well, I think originally for usual rings, for DG categories, but it can be defined in this generality over the sphere spectrum. Basically, what you need to do is just multiply C by perfect complexes on this algebraic simplices. These algebraic simplices are flat affine spaces. So formally, you take the tensor products of polynomials in one variable, and by polynomials, I mean the flat affine line. So S of x, S of one variable x, is kind of the monoid ring of natural numbers over the sphere spectrum. So formally, you attach this distinguished point, marked point to natural numbers and take suspension spectrum. So if you extend the scalars from sphere spectrum to Z, you get the usual affine spaces over Z. So you get the familiar homotopy K-theory. And you shouldn't consider free infinity algebras here. I mean, it's important that we consider just tensor product of copies of flat affine line.
Sorry, there is a question in the chat. The Barwick Mukherjee asks whether the theorem on the screen is true for any localizing, for any truncating invariant.
You mean if you replace KH by a truncating invariant?
Yeah.
No, I'm certain that already if you consider, well, first of all, you want it to be finitary at least. Otherwise, I think there is no chance. But even if it's finitary, even if it commutes with physical limits, no, it doesn't work like that. I mean, you can actually construct a counterexample. I mean, already if you consider the Dundas-Goodwillie-McCarthy theorem, then this TC for categories with structures, it's not well behaved. So you won't have such a theorem for K-inf. So for KH, it's kind of amazing fact that it turns out to be both truncating and also satisfies the theorem of the heart. But it's like very specific to this particular invariant. At least the proof is very specific to this particular invariant. Okay. So yeah, and also we use the devissage theorem for KH. So if we have a situation of devissage for abelian categories, then we have equivalence on spectra for this or on the level after applying KH. And this can be deduced actually from the above theorem of the heart using certain Auslander type construction. And I think I hope to mention it later if I have enough time. But it really can be considered as a corollary of the above theorem of the heart for KH. Okay, so now I explain what I mean by dualism. What I mean by duality between the theorem of the heart for KH and Dundas-Goodwillie-McCarthy theorem. So we can consider this universal finitary localizing invariant. So from small stable categories, small isomorphic complete stable categories to the so-called category of localizing motifs. It's also known as non-commutative motifs. So I have a paper where I study these categories of a general rigid base, and I prove their rigidity, and also I prove, I prove various results on how to compute morphisms and also some other interesting invariants. So I mean, it's quite a huge paper, which is quite difficult. But I'll just mention the very specific result, which is relevant for this duality. So we can also consider the localizing universal A1 invariant localizing invariant, and it would be more accurate to put flat here, universal A1 flat invariant localizing invariant. So this is actually a smashing localization of localizing motifs. So it has this right adjoint. So we call it. I like to denote it I upper star. So this right. It has right adjoint I lower star and another right adjoint I upper shrit. And it's also convenient to denote by gamma this global sections functor from A1 invariant motifs to spectra. So global sections is just home from the unit object. And so my result I mean, one of my results in this context states that for connective Ivan ring, this K-inf, so fiber of the cyclotomic trace, can be identified with global sections of I upper shriek of the motif of R. But on the other hand, if we just look at this, I mean, I didn't explain how this mesh characterization works, but actually, if you know the corresponding idempotent infinity algebra, then you immediately see that KH is obtained by a similar formula, but you, instead of I upper shriek, you apply I upper star. And here, for this category C, you don't need any assumptions or structures, just any idempotent complete stable category C. So we have this interpretation of KH. And so this is basically what I mean when I say that theorem of the heart for KH is due to the Dundas-Goodwillie-McCarthy theorem. I mean, it doesn't mean that you can apply this kind of intuition to any to all the possible results, but I mean, here it works really great. So you just naively replace I upper shriek with I upper star and replace truncating property for localized invariant with theorem of the heart. And here, surprisingly, it turns out to hold, but the proof is quite different from Dundas-Goodwillie-McCarthy. I mean, it has some similarities. Maybe I'll mention something later, but the proof is different.
May I ask one question? Yes. You know, there are these results that KH is like the derived global sections of K-theory with respect to this
topology.
Yeah, the CDH topology.
Yeah.
That K is somewhat related to the infinitesimal topology. So is that anyhow related to, I mean, does that show up here as a particular case of these two?
No, I think it's not. I mean, here, I mean, it's really a non-commutative story. I mean, here, I mean, when you consider CDH topology, I mean, basically when you deal with commutative rings, effectively you consider categories with symmetric monoidal structure. But here you don't have any monoidal structure at all. So I mean, it's like purely non-commutative. I mean, if you consider commutative geometry as a study of symmetric monoidal categories, then kind of non-commutative geometry is a study of stable categories without any additional structure. So in this case, I mean, okay, we have the structure of, we have T structure, but there is no kind of monoidal structure. So I don't think that there is interpretation in terms of some kind of, I mean, in terms of CDH topology or basically any topology in the usual commutative geometry here, at least from my understanding.
Okay, so there is no analogy.
I think not. Yeah, it's really about this non-commutative motifs, which
even for K-inf.
Sorry.
Even for K-inf, because for K-inf.
Even for K-inf. No,
I mean,
for K-inf,
this interpretation is non-commutative in the usual way.
No, I understand. No, for K-inf, okay, there might be. No, I don't know, but at least for me, it feels that like the way the analogy which I sketched, it gives you much better way to predict the results of this kind. Yeah, I think it's really you really need to consider the basic object of study as just a stable category, not related to geometry. I mean, I guess that's how it works in this context.
Okay, thanks.
At least from my point of view. Okay. So now I briefly sketch the more general version for the realizable categories. But it will be just a sketch. I will not give many details. There are many equivalent characterizations of this dualizable category, but one of them is that this is a presentable stable category such that the colimit functor from end objects end objects of C to C has a left adjoint, which is like another head. I mean, this is logical notation, so the right adjoint is just another, but this is like another head. Yeah, and so basically one can show that the image of the cyanide hat is contained in the incompletion of countable represented objects. So I like to use this omega 1 instead of aleph 1, but this is just aesthetic preference. So omega 1 is the same as aleph 1 here. So the continuous case theory is up to a shift. You do the following. You consider this. Oh, sorry, I did something wrong. I'll return. Yeah, just a moment. Okay, yeah. You take this incompletion of countable represented object, you model it by another head of C, and this is compactly generated case theory. So you take compact objects, so this is omega here, and then take usual case theory, and then take shift by -1, so the loops. So this is continuous case theory, which I defined in this paper about general localized invariance of large categories. And if C is compactly generated, then this is just case theory of compact objects. And for convenience, I say that dualizability category is a dualizable category C with a T structure compatible with filtered limits, such that this another head is T exact. So here I mean that incompletion of C is naturally equipped with T structure itself. Yeah, so this another head is required to be compatible with the structure, and also I require that C is generated by the heart as a localizing subcategory. So this is like the analog of small T categories, but for large categories. And the heart is, in this case, the heart is what I call coherently assembled abelian category. So this means that the K-limit functor from incompletion of A. Well, I forgot to mention that A should be a Grothendieck abelian category. So for this heart, it's automatic. So coherently assembled means that the K-limit functor has exact left adjoint. So not only the left adjoint exists, but it's also left exact. It's automatically right exact, but left exactness is a very strong condition. And then we have the realization functor from the unseparated derived category of the heart to C. So this is unseparated derived category. One way to define it is just as a category of unbounded complexes of injective objects. So this is due to Lurie. And if A is coherently assembled, then this unseparated derived category, I showed that it's dualizable, and so we can define continuous case theory as continuous case theory of the unseparated derived category. And if the category is locally coherent, so which is like familiar situation, then this unseparated derived category is just incompletion of dB of coherent objects. And this is due to Henning-Krause. So this is not Achim-Krause, it's Henning-Krause. And so we have this equivalence that continuous case theory of A is the usual case theory of coherent objects. And if this dualizable T category is compactly generated, then the T structure on this large category induces a bounded T structure on the compact objects. And the heart is just incompletion of the heart on compact objects. And so this realization functor in this case is just you apply incompletion to this familiar realization functor for small category for the small category of compact objects. And so if you have this picture in mind, then it's clear that at least you can formulate the above results in this more general setup. It doesn't mean automatically that they will hold, but at least you can formulate them in this general setting. But you have to be cautious, and I just want to give one example when this generalization is not automatic. So take some field and consider this abelian category of shifts of vector spaces on the real line. I mean, real line with the usual, with the classical topology. And then this category is coherently assembled. I mean, it's not obvious, but it's shown in my paper as a special case of more general effect. And this minus first K group is just Z, just integers. So we have coherently assembled abelian category, and minus first K group is non-zero. So this Schlichting's results on vanishing of k minus 1, so it doesn't generalize to this coherently assembled abelian categories. And there are many other geometric examples, like nuclear modules. Well, I will not go into details, but you can take nuclear modules from the formal neighborhood of nodal cubic curve, for example, or many other examples, which are much more difficult. But this is like the basic example, just shifts on the real line. But still, we always have this isomorphism. So minus first k group of the heart is the same as minus first k group of the category C, where C is any dualizable T category. So the proofs for these dualizable categories are more difficult, but the general ideas, at least main ideas, are the same as for small T categories. So I will just focus on the situation with small T categories. So now I'll try to give sketch some constructions which I used for the proofs. So first, there's a variation of this theorem which I formulated in the beginning. I formulated a certain theorem about co-connective, so to say, co-connective functors and some refinements of theorem of the heart and devissage. But you can also formulate a result like this, and this is actually a starting point for me. So you take some small T category, some non-negative integer, and consider this exact infinity category of objects in the amplitude between 0 and n. So the statement is that on k groups we have isomorphisms in degrees starting from minus n minus 2 and monomorphism in degree minus n minus 3. So yeah, C from 0 to n is exact infinity category in the terminology of Barwick. So the definition of this exact infinity category is due to Barwick originally. But the axioms are basically a generalization of equivalence axioms. And so this stable envelope of this category is also a small T category with the same heart as C. And in fact, we have a sequence of these small T categories with the same heart, starting from derived category of the heart. But then you have this infinite approximation of the category C itself. So the colimit of the sequence is initially equivalent to C. And one of the key ingredients for the proof of the theorem is just partial result. So basically surjectivity in degree minus n minus 2. And the proof is quite amazing. At least I was very happy when I discovered it. So I will just only give a main idea of how it works. So there is a well-known way to shift K-theory by one, so to categorify a suspension. Basically, not just K-theory, but any localized invariant. So this is like take countable int objects, mod out by the original category, and take idempotent completion. So this car means Karubi completion, idempotent completion. And here C doesn't require any structure, so any idempotent complete stable category. But if C is a small T category, then there is another useful construction which also categorifies the suspension. We can take simultaneous left and right completion for this T structure. And then it turns out that the K-theory spectrum is again a suspension of the K-theory spectrum of C. But if you take one-sided completion, like left or right completion, then K-theory would just vanish. But if you can take it both, like left and right completion, then it shifts by one. And this particular fact, I think it did not appear in the literature, but very closely ideas, very closely related constructions are in the papers of Schlichting and Antio, Gepner, and Heller. And then direct computation shows that the isomorphism between minus n minus first k group of this E and minus n minus second k group of C is induced by a certain non-exact but additive functor from n plus first iteration of Kalkin to n plus second iteration of Kalkin. Certain residue categorification of a certain residue map. And then this functor turns out to have surprising property. Its essential image is just contained in the essential image of the functor from n plus second Kalkin category of stable envelope of this C from 0 to n plus second Kalkin category of C. And this already gives you the lemma. So this already gives you the surjectivity on the -n-2nd K group. And the proof requires a very careful analysis of these T structures which naturally arise on iterated end objects. So for example, this iterated Kalkin category usually doesn't have any natural T structure, but its incompletion has a natural T structure, and these are used like in a very careful way to prove these statements about essential images. So this is the surjectivity in degree -n-2. And then if you have the surjectivity, there is a, I mean, to deduce the theorem, I use countably many short exact sequence of categories, and they're also they're also quite interesting. So the idea is that for strictly positive n, you can consider this different exact category C tilde from 0 n. You just require that a boundary map from pi n to pi n-1 vanishes. So this is you have fewer short exact sequences than in the original category C from 0 to n. Then for this auxiliary category, for a stable envelope, you have semi-orthogonal decompositions into stable envelope of C from 0 to n-1 and the derived category of the heart. And you can construct, I mean, you naturally obtain this short exact sequence, but this kernel of this functor, localization functor Tn, it turns out to be also a category with a T structure, with a bounded T structure, with the same heart as C. And it's also approximated very nicely by the derived category of the heart. So you have isomorphisms on X groups in degrees up to n+1. So all these facts can be proved by careful analysis of these categories. I mean, it's not very difficult after this is formulated to check that all of this holds. And then it turns out remarkably that this is already sufficient to prove the theorem. So together with the lemma on K -n-2, if you carefully analyze this long exact sequences, I mean, you use certain double induction and you go to the K-limit like a few times during this induction, but then, I mean, the proof is quite natural. So, I mean, basically using this picture, you can prove the theorem just starting from the surjectivity in degree -n-2. So this is this refined theorem of the heart for this. I don't know what's a good name for it. Maybe a theorem of the amplitude. I don't know, but I just called it refined theorem of the heart. And I want to briefly mention another crucial construction for the proofs, which is, I think, which is might be not intuitively clear for people who did not work with these abstract categorical constructions, but the construction is very general. So I consider some. It's convenient to define this notion of -n co-connective functor between small T categories. So first it's required to be exact and T-exact. Again, I have this condition that f of C generates the target as an idempotent complete stable subcategory. It's basically the condition that appeared in the first of the theorems. I'm just spelling this out again. And then the condition on X groups can be formulated saying that cone of the map between spectra of morphisms from X to Y and from f of X to f of Y. So this cone is -n co-connective. So it's basically just rephrasing the condition which I stated previously for X groups. And then for such functor, you can construct a natural approximation of D starting from C. So this is a sequence C0, C1, and so on. So all these categories are equipped with bounded T structures. Actually, all these functors are T-exact, and the K-limit is identified with D. And these functors, I mean, the construction is organized in such a way that this functor from CK to CK+1 becomes more and more co-connective. So you have this exponential growth. Well, There is a particular case n equals 1 when you don't have any growth if n equals 1. But this is like, very special case, but normally I apply it when n is at least 2. And then you have exponential growth, which will be important later. But at least all of them are minus n co-connective. And then another important fact is that if you consider this monad, just take int objects and take the composition of the right adjoint to this int of gk and int of gk. So this is a monad on int of ck. It is obtained from some E0 algebra in the category of end functors by a left adjoint to the forgetful functor. Again, I mean, this kind of intuition might be I mean, people might not have intuition to think about this, why this is important, but this situation is actually when the monad is like this, it's much simpler than the general monad. So this is like a very particular class of monads. They are kind of deformed tensor algebras, and it's much easier to work with them. And so basically the intuition is that each of this transition functor is kind of Cauchy dual to a square zero extension, if we continue this analogy with connective Ivan rings. And because of this very special property of these transition functors, I was able to construct certain short exact sequences relating these categories, and eventually prove that under these assumptions on the functor, the cone of the map from K-theory of C to K-theory of D is minus n minus 1 co-connective. So this is what I promised in the first of these theorems. So this result, and of course it's based on the refined theorem of the heart, which I already sketched, which was a statement about C from 0 to n. Okay, so this is like very roughly the idea of what kind of constructions are used in this proofs. And using this general constructions, I was also able to prove the theorem of the heart, but in a much more precise form. So theorem of the heart for KH. So basically KH is a complicated calimit over all simplices, over the category delta opposite. So it's geometric realization. But I mean, to prove such results, it's convenient to deal with finite calimits. I mean, they're kind of much simpler. And so I consider this filtration on KH, the standard filtration on the geometric realization. So this is just calimit over simplices of dimension at most k. I just call it UK. For some reason, I don't know. I just don't know if there is a standard notation for this, because I looked at Weibel's paper. I think there is no standard notation for this filtration. I just call them by UK. I needed some notation for them. Okay, and then the more precise version of the theorem of the heart is the following. So if you have a minus n co-connective functor, and you have some non-negative integer m, then you can consider cone of UK of f. Sorry, I forgot to say k and l are some non-negative integers, and k is less or equal to l. So I have the sequence like cone of UK of a, cone of UK of f, indexed by natural numbers, and I want to know that calimit of the sequence is 0. But this is difficult, so I need a more precise statement. And the more precise statement is like this. I take truncations of these cones for some k less or equal to than L. And I prove that the map on these truncations is null homotopic under these conditions on C and the difference between L and K. And so again, I have this exponential growth here, but it appears naturally somehow using the approximation which I mentioned previously. So this is like, and I think that this result is also sort of sharp. I mean, of course, it's difficult to give examples, and maybe I don't have motivation to give examples, but it looks like a sharp result that you cannot really improve this estimates. And the case n equals 2 directly implies the equivalence between KH of the heart and kh of c. So just because realization functor is -2 co-connective, it's well known that the map on X2 is a monomorphism. Yeah, so you just directly apply this theorem, and because of this exponential growth, you see that the colimit of the cones will be just 0, which is exactly what we need. So the proof is quite tricky, and like I'm actually proving it together with a similar statement, but under this very specific assumptions on the monad. So when you have this assumption on the monad that it comes from E0 algebra in ender functors, then there are also some similar estimates, but they are better. And the induction goes like I prove both of the statements by induction on this parameter m, this non-negative integer. So this is roughly like the general idea. And I want to say that you can actually, suppose that you don't know anything about Dundas-Goodwillie-McCarthy theorem, then you can still prove, using similar methods, you can still prove, you can still prove the truncating property for this invariant gamma of I upper shriek of U log of R. So just if you don't know this, if you don't know Dundas-Goodwillie-McCarthy, if you don't know my theorem about K-inf, just consider this invariant gamma of I upper shriek instead of gamma of I upper star. Then you can actually prove using similar methods the truncating property for that invariant. So it's also an interesting point of view on this Dundas-Goodwillie-McCarthy theorem. Okay. And I forgot to say, induction step here is quite interesting. It uses actually A1 homotopy for monads. Basically, very roughly speaking, the idea is that if a monad has additional non-negative grading, then it is the same as multiplicative A1 action, and it can be contracted to the component of degree 0, of weight 0. And this kind of construction is used here in the inductive step. So, I mean, as you see, quite a lot is happening here. So the proof is quite tricky, but eventually all that I'm using is the localization property for K-theory, the commutation of K-theory with colimits of sequences, and the knowledge what is K0. That's basically everything that I use in all these arguments, in all the results which are formulated here. Okay. And just finally, I want to mention the sharpness of the estimates. So I work over some field, and it doesn't matter what is K. You can take any field without any assumptions. So first, there exist small abelian categories over K, such that the inclusion is exact, and each object of A is an extension of two objects of B. So the situation of devissage, but stronger, just extension of two objects of B. And such that the map on the -2nd K group is not surjective. And this is the idea is very similar to Niemann's example of abelian category with non-vanishing -2nd K group. So I'm taking a cuspidal cubic curve, and so I'm taking the exact category of vector bundles. So vect X is just finite rank vector bundles. And I take B0 to be effaceable functors. So what I mean, so this effaceable functors, maybe more precise term is finally presented, effaceable functors. This is abelian category, so this full subcategory of functors, which are cokernels of representable, morphisms between representable functors induced by admissible epimorphism of vector bundles. And then I'm taking the category of pairs, just an object of this B0, effaceable functor, and the nilpotent endomorphism. And similarly, you have a filtration. So you can consider pairs where you restrict the degree of nilpotency when f to the power n+1 vanishes. And then by direct computation, so cokernel of this map on K-2 is the same as -1st nil group of B0, which can be shown to be the same as zeros neat group of the cuspidal curve, but it is a countable dimensional vector space. So it's xk of x. So it is non-zero. And it follows that for, at least for some n, this map from minus second k group of Bn to minus second k group of Bn plus 1 is not surjective, which give an example for this theorem. At least for any n, this map is not surjective, and the cokernel is one-dimensional space. But this requires some more work. Okay, and just finally, I want to explain that the theorem of the heart fails for minus third k group. So it's based on the example in the previous theorem. So take any example in the previous theorem. So you have this non-surjectivity on the minus second k group, and then you can do the following construction. Consider this category of pairs, an object of A, and a sub-object such that both the sub-object and the quotient are contained in B. So this is a quasi-abelian category. In particular, it's exact category. So its derived category can be decomposed into two copies of derived category of B. And I define this T category, which will be an example. I define it as a kernel of localization. I have localization from dB of this quasi-abelian to dB of A, just forgetting the sub-object. And then it turns out that this kernel has a natural T structure, bounded T structure, for which the heart is equivalent to B. So this heart consists of objects like cone of the map from m, 0 to m, m. And a long exact sequence of k groups, so basically gives you this non-surjectivity on k minus 3. So the quotient of k minus 3 of C modulo k minus 3 of the heart surjectively maps onto the quotient of k minus 2 of A modulo k minus 2 of B. I mean, of course, to see this, you need to analyze, you need some analysis of this short exact sequence of categories, but it's really not very complicated. And so this gives an example which shows the theorem of the heart naive theorem of the heart fails for k minus 3. Okay, I'll stop here.
Okay, thank you very much for a very thorough talk. Are there any questions from the audience? Well, it seems we ran out of questions. I just a silly question. What you are in the Steklov Institute, right?
Yes.
And but what does the acronym MIAN mean?
It's Mathematical Institute of Academy of Sciences, but sciences is nauka in Russian.
Okay. Yeah. Great. Well, I said it was a silly question. Okay. So here we have a question by Devarshi. Are there interesting examples of dualizable T categories in analytic geometry?
Yes, there are. And basically in the paper, I only covered very basic examples like nuclear solid modules over ZP. And of course, it automatically implies the same over QP. So this is a basic example of a dualizable T category.
Can you describe the heart in that case?
Well, it can be described as a certain category of almost modules, but in this non-commutative setup. So basically you take, just explicit answer is the following. You take Banach ZP module with countable topological basis over ZP. You take the ring, just abstract ring of bounded operators, and then you take the ideal of compact operators, which are the same as straight class operators. And then this is a situation of non-commutative form of mathematics. And so you just take so this ideal squares to itself, and it's also flat on one side. As far as I remember, as a right module, it's flat. So this is a situation of almost mathematics, and so the heart will be the category of almost modules.
And can you say anything in the complex setting?
I think I can, but I need to double check the computation. So basically, you can interpret nuclear gaseous complex vector spaces similarly, but now you take Hilbert space, again, like separable Hilbert space, L2 of sequences, and you take the abstract ring of bounded operators, and you take this ideal. You take ideal of compact operators such that the singular values have quasi-exponential decay. And then, again, I need to double check this, but I think again, the analogous statement still holds. So you get this dualizability category, and the heart is described in the same way, but for this ideal.
Okay.
Is it clear? Is it clear what I said?
Yeah, sort of. And can you say anything about the K-1 of this heart?
No, I mean that's a modified Koch conjecture for the point. I mean K-1 of the, which I think Dustin proved. I mean Dustin and some other people already thought about non-positive K theory, but it's very difficult for positive K theory. But I mean, kind of K-1 of the heart is the same as K-1 of the ambient category in this case by my result.
Sure.
But also in this case, I think, again, I need to double check this, but I think the realization functor is just an equivalence.
Ah, okay.
But yeah, in the Archimedean setup, this computations become, of course, more difficult. Yeah. But still, I think this works.
Okay, thanks.
Mm-hmm.
Okay, are there any further questions? If not, we thank Sasha and end the recording here.
Yep. Thank you.
Okay. So thank you very much.
Yeah, thanks. Thank you for the questions. Yeah, just to stop me.
Yeah.